Recording in progress.
Okay. I think I got it fixed up. All right, let's see. All right. Okay, let's see. Let me share my screen here. Oh boy. All right. I think I finally did it. Hey everyone, just a reminder, this is being recorded. I'm probably going to put it online. So if you don't want to show your face, then don't. I kind of recommend that, like, when we're interacting though, I mean, you can type in the chat, but like I kind of suggest you nevertheless just vocally pipe up, because I don't know, do you really care if your voice is in the video? And it might be easier than typing. But if you want to type, that's fine too. I got the chat up. Yeah, how's it going? Does anybody have any question about CS theory? No, you got everything solved?
Could we talk about number 3, perhaps?
Sure. Number 3. What's number 3? Number 3 was, oh, you have a sequence. Let's see, 1 equals A1 less than or equal to A2, less than or equal to A3, less than or equal to AN. And it satisfies AI plus 1 minus AI is at most square root AI. And you want to bound sum of AI plus 1 minus AI over AI. I goes from 1 to n minus 1 by log n. This one, yeah. Yeah, let's see, what about it?
Yeah, so I guess I started by assuming equality for the inequality.
Okay, that's reasonable. Let me just, I haven't thought about this problem in a while, so I always love this situation when, like, I myself don't remember how to do the homework, then I can just think about it right along with you. Yeah, that's natural. Now, it's not super clear that you can do that, but it's definitely a natural move. So yeah, let's imagine hypothetically, say that AI plus 1 minus AI equals root AI. I mean, it's good to check that you're in okay shape in this case, for sure.
Yeah, intuitively, it seems like that should be the worst case, but.
Yeah, hard to say. Well, let's think about it later, but like, okay, suppose this is the worst case. Then what are you thinking?
Well, so I just started. You can plug it right into the summation, but.
Oh yeah, I guess you can just like literally compute, I suppose. I mean, like A2 would be 2. And then like A3 would be like 2 plus root 2. A4 would be like, it's gonna get not too enjoyable. Okay.
Yeah, and then you can substitute in to the actual summation term.
Oh, but wait, I guess it's not so bad, right? Because like this thing here is this thing here. So if you assume this is true, then you have sum I goes from 1 to n minus 1 of root AI over AI, which, okay, that's like sum I goes from 1 to n minus 1 of 1 over root AI. Okay, that seems not too bad.
Yeah,
now
this is
what,
where I'm. This is where I'm quite stuck. I don't really know what to do from here.
Okay, let's see. Well, Yeah, how could things go wrong? For example, well, you might worry that like, okay, you might worry that like AI is, I don't know, less than 2 for all I. That's not a for all. And then you'd be very sad because like this quantity here would be like between 1 and √2. So this whole fraction would be like, I don't know, some number. It'd be at least like 0.7 or something. And then the whole sum would be like 0.7n, which would be bad. But can that happen?
I mean, we're adding stuff, so hopefully not, but I don't know how to tell yet, at least.
Well, must AI get large? I mean, I guess it was already like this big up here. It was like 2 plus something. Here was like, I don't know how much this is, 3 point something. I mean, do you know like what AI is approximately like in this case? Oh wait, there's chat. We could try to plot. Yeah, we could try to plot it. Let's do it. Says the chat. Who wants to do it? I guess I'm the only one like, well, somebody would, I don't know, is somebody like real cool and they can like share their screen like plotting it? Or is it gonna be like infinitely slower than if I do it? Let's all do it together. You try it on your computer. I'll try it on my computer. We'll do it together. Let's see, I'm gonna have to like share my screen over here. Hold on. Let me get my favorite math program open, AKA the Canadian Mathematica. I'll share my screen. 1 second. Cool. Okay. So let's see. How do we do this? I guess we're like, let's make a list called A. And we'll start it at 1. And then let's make like N 50. I don't know. And then we'll go for I equals 2. I guess it doesn't matter. 2. Oh wait, you have to do this from 2 to N. And then we'll be like A. Please add to yourself a new number. And a new number should be A, I minus 1. What is it? Plus, no, square root of, is this? Plus square root of I minus 1? Should have just made it go. Whoa, okay, I should not have done that. Let's do this. First of all, let's make it go up to 10 so we don't go crazy. Okay. Okay, that's plausible, right? Is this plausible? Is this consistent? Somebody say like, yes, this is consistent with my experience. Oh wait, it's good. Somebody's got it going. I plugged into Wolfram Alpha and it gave me the first 5 values and I didn't know how to get any more. Somebody in chat says, yeah, on Mathematica, it's very slow as the first few. Yes. Okay, great. Yeah. Well, okay, yeah. If you're using like Mathematica or like Maple or something, like it's probably going to be like, oh, I can compute this exactly, and it'll have like, you know, like 1,000 nested square roots, which is, I mean, it should be able to handle that. I mean, come on, it should toughen up, but I can understand how it might get slow. So you might want to like tell it to be like, yo, please do this with like floating point rather than trying to like literally compute it algebraically. Okay, so now if I was good, I would be able to just like plot this. But I think if you just like type this, like it goes wrong. You have to do this like annoying thing where you're like, okay, let's just say points are like a sequence of like I and AI. As I goes from 1 to N. And then I think we can now plot this. Okay, so it looks like something. Let's beef up N now to like 100. Actually, let me just make this 1.0 because then it'll do everything in floating point. Not that it really matters, but okay. Okay, it's doing something. I mean, maybe it's a parabola. Does anybody want to like eyeball this? Try to figure it out. Probably if we like want to be like, I mean, does somebody have a suggestion on like a principled way to try to guess what the growth rate of this is? Actually, you could just plot its log. Yeah, that's a good idea. So let's see, let's do like, we should probably, okay, let's like hypothesize it looks like a parabola. I mean, who knows? It could be exponential for all we know. Yeah, guess x to the c and compare the ratio of the values. Oh, that's a good idea. Yeah. Okay, so let's say if it were like, you know, n to the c, and then we logged it, we would get c log n. And then if we divided by log n, we'd get c. So let's like make the log version of the points where we're like, hey, please give me these points. But let's be like, let's log this and then divide it by, whoops, divide by log n. That's going to be not so great when n is 1. So, oh, wait a minute, this should say log I. So let's just go from 2. It's fine. Oops, I should have given that a different name. Let's restart this. Let's call this log points and let's plot this. Okay, it seems to be flattening out, which is pretty good. I mean, that's good news. Let's make it go up to like 10,000. Why not? Let's definitely not print it out though. Oh, it's taking a long time. Oh, no, it's not that long. Okay. We can do this. Okay. Well, it's gone up to like 1.8 something. I mean, on the principle that like probably life is nice, it's probably like 2. I mean, it seems to be bounded by 2. So I suppose that we could speculate that it's at most like, you know, that an is at most, well, let's say constant times n squared. Actually, I suppose we could like, okay, if we believe that it's at most n squared, let's plot that's that. Can I like overlay? Okay, this is showing my bad knowledge. I just want to like overlay 2 plots. Let me just say squares, sequence. This is not the right way to do it, so I apologize, but it's a fast way to do it. Let's just make the squares. And let's plot. Is this gonna work? Okay, I don't know which is which now, so let me do color. Let's make the squares red and the other ones blue. Okay, so it actually looks like it's less than, I mean, the squares seem to be beating the actual sequence. In fact, like what if we do like, instead of square, we can do like 0.5 I squared. Whoops. Seem to even be beating like 0.5 I squared. Well, anyway, I mean, 0.4 I squared. I wonder if it's like literally beating it for like every single n. Let's make n only go up to 20. Doesn't seem to be beating it for like right at the beginning. The reason I'm thinking about like having it, you know, okay, we know it's like big O of n squared, but like I'm imagining how you might prove that. And like if you really want to prove it's like big O of n squared, it's convenient if you're like, oh, it's like literally at most, you know, 10n squared for every single n. Because that could facilitate a proof by induction, maybe. Oh, but that's because I put this 0.4 in. What if I put like literally, maybe you guys can't tell what I'm doing anymore, but aha. So this one you put is like, when the red is like literally n squared, seems kind of good. So it seems to be like literally at most n squared. Let's see if we can prove that out. Let me share my screen over here. Hey, I'm back. Let's see what's going on. Okay, so we like kind of believe that. Okay, so like conjecture is that like under this hypothesis, star, we kind of think that like maybe, well, I guess if it's a conjecture, we don't have to write maybe. So it's very speculative. No. Maybe an is at most n squared. Seems pretty true. I mean, this was like 2. This was like 3 point something. Seems good. Yeah, any thoughts? Any idea how to prove that? Oh, Bernardo says something in the chat. Maybe Bernardo just like literally wrote a proof. I'm not sure. Could be. Okay, so we have one person like suggesting a proof, one person suggesting induction. Yeah, I kind of imagine you can prove this by induction. Well, it's not clear, but it's what I would try, and it might work. So, okay, in lieu of me solving the whole problem, let me just say, perhaps you could prove this by induction. I mean, it's definitely true, right? I mean, by virtue of our plotting, it's definitely true. So that's reassuring, right? Like that's half the battle. Like now you know that it's true. How are you gonna prove it? Well, hopefully induction works. But okay, let's move on for a little bit. Like let's hypothesize that it works. So is that good? Does anybody have any thoughts on whether this helps us in life?
I mean, that would pretty much give it to us, right? Because we could plug it back in and we'd get the harmonic sum.
Yeah, that's true. Well, here's the weird thing,
is the
right?
inequality going the wrong way?
Inequality is going the wrong way.
Yeah.
Like if an were like, let's say if an, yeah, actually you want this, right? Like if an were like at least, I don't know, 0.1 n squared, then 1 over root a n would be, see now it's in the denominator, so you get reciprocal like most 1 over square root 0.1 n, okay, which is like some constant times 1 over n. And then, yeah, then we know if you like sum this up to n, you get log n, right? So, okay, so maybe we were like trying to do it the wrong way. Like maybe we wanted to show that an is at least this, which also seemed true, right? Like it did seem to be growing quadratically, maybe with like a smaller constant. But then, okay, so like perhaps we could try to prove that too. Although then, you see, it's funny because then this like kind of maybe messes up your intuition that like, this is all under the hypothesis that like the inequality looked, I mean that the inequality was exact because there was some feeling that this would be the worst case. And then but then like this kind of messes with your inequality because like, it messes with this intuition because like we saw here, we got sad if AI was too small. Somebody says, with the given constraints, all AIs could be 1, and hence we can't expect such an inequality. Yeah, that's a good point, says person in the chat. If all the, all the AIs could be 1, and then you would certainly not have that the nth one is at least 0.1 over 0.1 times n squared. And then you might be like, oh no, I'm like dead. Because then you might say like, oh, but then like, oh, this thing, like this thing, the sum of 1 over root AI would be like sum of 1, and it would equal n, which is way bigger than order n log or order log n. And you'd be like, oh no, I'm dead. But then you're not really dead because like this was not actually the thing we were summing. We were summing this. And if like all the AIs are 1, then like the actual expressions are all 0. So there's that. I kind of feel like it's nevertheless like a good start. Like, you know, the things we did were not wasted in the sense that like, I think by pushing this forward, you could show that if this were literally true for all I, then you're in good shape, because then like the A's will like grow quadratically, and then this sum will act like a harmonic sum, and it won't be too large. And then you have to say like, well, the only other case is like, well, the infinitely many cases when this does not hold exactly with equality. But there is still some feeling, right, that like, oh, perhaps it's good in that case, because I mean, well, if it doesn't hold with equality, then like this numerator is like smaller than it could have been. Yeah, wow, this one makes it a bit of a problem, but something. Anybody who has not already solved it have a suggestion? Or alternatively, we can just pause on this problem for a while and talk about something else. A person in the chat who I know has solved it has said, I think the inequality can get pretty tight, even if the sequence AN converges to a limit L. Let's see. Yeah, so I mean, it could be that like, you might worry that like yeah, it could be that, okay, so we kind of know with this inequality, right, that like A's can get bigger and bigger and bigger. Like we've kind of seen that like if you like hit the inequality like with exactly every time, then the A's start to go quadratically. So you could have like the A's like kind of grow for a while, but then you could decide like, oh, I'm going to stop hitting the inequality. Like maybe I'll have them like, I don't know, a bunch of A's in a row be the same, which is consistent with the inequality. Now, if you have a bunch of A's in a row that are the same, that's not like hurting you, because this numerator will be the same every time. Or sorry, this numerator would be 0 every time. Yeah. Yeah, it's a funny thing, right? Because like, it's interesting. I think it's an interesting illustration of like the greedy algorithm going wrong, which, you know, it can happen, right? Like, let's say like, you know, you looked at the sequence of A's for a while and they went up to some thing, and like now you're on A27 and it's like 11. And then like, you know, your worst enemy gets to choose the next A. And what would your like, you know, if your worst enemy was being greedy, what would they choose for the next A? They'd be like, okay, like as I choose this next A, like maybe I'm choosing AI plus 1. You know, this sum, they've paid some amount already, and now they're going to pay AI plus 1 minus AI divided by AI. And your worst enemy is like, okay, this AI has already been fixed. This AI has already been fixed. What's left over is my choice of AI plus 1. I may as well make AI plus 1 like as big as I can in order to like, if I'm being greedy, to like make the owner of the inequality pay like the most like right now. And so that does suggest the intuition that like, oh, like things are worse for you, the inequality prover, if AI plus 1 is always like as big as it could be, like the greedy thing. But like, I think this is an example, right, of like greedy going wrong, or at least greedy, maybe this is the worst case, but like, you see, like, it's not so clear you should be greedy, because like, if you make AI plus 1 like as big as possible, yeah, that works well. But like in the next round, like now the new like AI is like smaller. So like in the future you is going to be able, if you're the adversary, like future you is going to be able to force less gain. That's tricky. Let's pause there for a moment. We can come back to this problem, but like maybe, does anybody have a question, a different question?
Yes, I'm having some problem on 1.2 part B.
1.2 part B. Allow me to remind myself what is 1.2 part B. Okay, let's see. This was question, I'll write it here. This was question 2. It was about, oh, you have like a read once DNF. What is this like? It's like an OR of like wide OR. I should really write these problems down before we start to save time. What is this? S? And then like you have a bunch of ands here. And these have width W. And these are going down to the variables x1, x2, dot, 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 x, n, where like n is s times w. And okay, so there's some exact probability that like this is true, probability that the output is true. Okay, even though this is like part A of the problem, like I assume you can do this part. So can somebody just tell me what the answer to this is?
I can say what I got. So
sure.
I got 1 minus, and then between parentheses to the power of s, 1 minus a half to the power of w.
That looks pretty right. If that's not right, then somebody pipe up in the chat. But if everybody agrees, then I guess it's correct. Okay, and then part B is like, oh, we would like this to be as close to a half as possible without going over. Okay, so we're interested in this thing being around a half, which I guess is the same as like this thing being around a half. Okay, and then for each W, like let's say I take W to be 50, let S be the largest integer such this is true. Okay, let's not stress for a moment about like things having to be integers, because that's always very annoying. I don't think it's the part of the problem. Oh yeah, because it wants to compute S. The problem wants you to compute S. Okay, so like given, it's like given, basically the problem is like given a fixed W, you know, what is S, which is gonna be a function of W, such that this thing is about a half. And okay, maybe S has to be an integer, but like the question is only asking you to get this up to plus or minus order 1. And so like rounding off a number to an integer changes it by less than 1. So we'll not worry about that. So basically we have this problem, like W is kind of fixed. Like W is fixed. And we want this expression to equal a half. And we're like, what does that force upon S? So far so good. Okay, so do you have a particular question or?
No, I'd say that from this point on, my ideas didn't take me anywhere, basically.
Okay, well, what were your ideas?
You know, first it seemed like maybe I could make it in some way look like the limit definition of E, but then the sign is changed and it would just mess things up.
I see, the limit definition of E. Okay, let's see, E, probably you mean this one, right? Like 1 plus 1 over n, whoops.
Yes, exactly.
To the n, well, it's not equal, but it like this thing, I've written it in a funny way, goes to E. Yeah, well, this is a good suggestion because it certainly resembles it, at least somewhat, right? I mean, you have like 1 minus something that's like small. Here you have like 1 plus something that's like small. But okay, somewhat. And then you're like, oh, but if I raise this to this big power, you know, I want to like, okay, if you have like 1 minus small, you square it, it's still, you know, it's like 0.999 squared, that's still close to 1. And then you cube it, it's still close to 1. But like eventually, as S gets bigger, like 1 minus small to the power of S will get all the way down to a half. And we kind of have like a similar situation here where you have like, if you have like 1.00001 and you square it, it's still close to 1. And you cube it, it's still close to 1. But eventually it'll like get away from 1. Yeah, a suggestion in the chat is solve for S and plot it. We could do that, right? So in fact, you know, in some sense, you can just solve for S, but, you know, the question is asking you to like, kind of compute like a standard form asymptotic for S. So you could be like, oh, I could like log both sides. I could take, yeah, I can be like S. I mean, okay, if you're really like, just brute forcing it, you'd be like, okay, I'll take log base 2 of both sides, half to the W equals -1, and then like S equals -1 over log base 2, 1 minus a half to the W. And then you could be like, well, that's all well and good, but that's kind of disgusting looking. We're trying to show that, you know, S is like asymptotic to some like nice expression. So the suggestion was, yeah, again, we could like plot it and then try to figure out what the answer is. And then that would be nice, right? It's always reassuring to like kind of feel you know what the answer is, even if you're not sure how to prove it. But I kind of want to like go back to the original idea, which was kind of make this look like this. So I mean, I know one thing one could do, but yeah, I think your suggestion was that like, unfortunately, like this is like a minus and this is like a plus. I guess what you need to know is the following. Yeah. Well, do you know like any variations on this that could be helpful to us?
You mean other variations of the limit or of E?
Yeah.
We could tend towards the series definition of E, I guess, but
Yeah,
we'd still need, that doesn't solve the problem of making the negative thing positive.
This one, you mean?
Yeah, but I'm not sure that helps. I'm not sure I understood what you wanted.
Well, I don't have something specific in mind per se. Although, well, actually, I mean, here's like an observation. If you take, okay, if you just say that like intuitively 1 + 1 over n to the n is approximately E, we can take the reciprocal of both sides. So then like 1 over 1 + 1 over n, the n is approximately e to the -1. But this is like, this is 1 over 1 + 1 over n to the n. And what is this approximately equal to? I mean, actually, if you really want to be like, sorry, go ahead.
To 1, I think it's minus the 1 over n plus its squared, something like that.
Yeah, exactly. Yeah, if you have like 1 over 1 plus small, that's basically 1 minus small. I mean, that's the first approximation. You know, 1 over 1.0001 is about 0.999. Actually, I mean, I guess you could literally say, okay, this is 1 over, just clearing the denominators, n plus 1 over n, also known as n over n plus 1. And if you imagine, oh, this is close to 1, you're like, oh, it's like n plus 1 minus 1 over n plus 1, which is 1 minus, sorry, 1 minus 1 over n plus 1. So indeed, from here, we have that like 1 minus 1 over n plus 1 to the n is approximately e to the -1. Let's look a little closer actually, because, you know, now you see how like, oh, here we have like 1 minus something raised to a large power. This is, approximately 1 over e. I don't know what that is, 0.67 or something. Or no, 0.3 something. So that's more similar. Yeah, I guess what I just did there was like kind of similar to just taking x to be minus x here. So e to the minus x is like 1 minus x plus x squared over 2 factorial minus x cubed over 3 factorial plus dot 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 dot. Yeah. So do you see how this might help?
Yes, now it seems closer to a solution.
Seems closer, right? I mean, your first instinct is like, okay, great. So 1 minus x is approximately e to the minus x. Like this is kind of, our favorite approximation in the world. 1 plus x is approximately e to the x, but, I replaced x by minus x. So that may make you feel good here. Okay, so there is the issue that like this is not literally correct. So I mean, we got to like come back to this. But okay, let's just press on as though this were true. So then we'd be like 1 minus a half to the w to the s, I mean, is approximately 1 minus, oops, sorry. It's like we're taking x to be this thing. So it'd be like e to the minus a half to the w to the s. And like the reason, okay, so like why were we messing around? Like the reason this turned out to be a good move is like now something like nice happens in the exponent, because the laws of exponents, we can say like, oh, this is literally equal to e to the minus s, well, times a half to the w. Let me just write that as over 2 to the w. Okay, so albeit we made like an approximation here and we have to worry about what the error is. We've got this like expression looking nicer. So this is like another, like, it's kind of like life rule that like, okay, if you have like the sum of some, like maybe like 1 plus something small, positive or negative to a power, that's kind of gross. So like, it's nice to make the base of the exponent look like e to the something, because then if you take like a further power, the exponents just multiply. Like this is what's happened here. Okay, so then, if we believe that, then we're trying to set this thing equal to a half. Well, again, we can brute force solve this, but like it works better this time, right? Because like, okay, I'll take the reciprocal of both sides, get e to the s over 2 to the w equals 2. Now, since the base of the exponent here is e, I should probably take the natural logarithm. So I'll take the ln of both sides and I get like s over 2 to the w equals ln 2, which is some number, 0.6 or something. And what were we doing solving for s? Oh, we get like s equals 2 to the w times ln 2, which is nicer. So like this would count as like, standard form. Like if we had exactly had this, it's just, the parameter here is w, it's like some constant times another constant to the w, which is good. Now we're still not done. Like we have to suffer because we're like, oh, well, I mean, we made an approximation here and we have to like worry about the extent to which that approximation is correct. So, okay, like you have to, basically the thing to do, and like, okay, I won't like solve everything right now, but like the thing to do is like, say like, okay, well, this is around e to the whatever 1 over 2 w, but like maybe plus or minus some error term. And we got to deal with that error term being there. And actually now we have like the same phenomenon. Let me just repeat this. Like, we got like e to the sum blah, 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 which made us happy. And then we raised it to the s and we're like, oh, that's equal to e to the blah, blah, blah times s. And we're very happy. But now we're like, oh, shoot, there's like an error term. Like this wasn't really e to the whatever, 1 over 2 w, 2 to the w. It was some like nice thing plus maybe some error. And like now we have this and we're like, oh, we're back to the same like annoying situation where we're all happy to like, do this. But we got this stupid plus here. Now what? Well, same thing. Oh, a person asks, can we replace the approximation with a less than or equal to? Yeah, probably. So like, this like 1 plus x is approximately e to the x. It has some I mean, I guess like this is literally true for at least for positive x. For negative x, maybe I have to think about it. Well, let's see. E to the x looks like this. Like 1 plus x looks like this. So I guess it's like literally true for all x. But you know, you kind of need like a two-sided inequality because like we're trying to figure out the asymptotics of something. So like we kind of need to know that this like approximation is like not only not bigger than the truth, but also not smaller than the truth by too much. Okay, so all I was going to say here is like, I mean, I'm not going to solve the whole problem, but like you want to like do a similar thing where you convert this plus to a times because you're exponentiating. So you're like, oh, if only I could write this as like e to the something times like maybe 1 plus tiny. And then if I raise this, I mean, this is maybe a step that one needs to do. If I raise this to the power of s, then we get e to the blah, blah, blah times s, which makes us happy. It's a nice expression, times like 1 plus tiny to the s. And now we might hope to show that like this is small, which is basically true if tiny has to be like less than 1 over s. And again, you could be like, oh, this is roughly e to the tiny. And so like, but okay, let me not quite solve everything yet. I mean, we can come back to this. But that's how one can make progress. Alternatively, like, once you're here, I mean, all the things we've been doing are not too dissimilar from saying like, oh, like, let's understand like the Taylor expansion of log. So like, it's also true that like log of like 1 plus tiny is approximately tiny. And that can make things simpler in your life too. But again, you have to, you're not quite done because you have to worry, what does this approximation mean? You know, it's like up to like plus or minus tiny squared times a constant maybe. But I guess these are some of the ideas you'll need. Great. Any other question? How about another question? Or we can go back to something we've already talked about. I bet there's another question. I bet not everybody has solved every problem. Or you can ask about something like not on the homework, about the lecture. Part E for 1. Oh, thank you. Like, yeah, otherwise I would just have to be reduced to start chatting. Like, how's your day going? My day's going okay, by the way. Part E on number 1. What is part E number 1? Oh, problem 1 was about the prime number theorem. How nice. Let's see. I'll just read it. How many factors of 3 are there in 100 factorial? 100 factorial. Well, that's not the question. It's like a rhetorical question that the problem starts with. It's 100 times 99 times 98 times 2 times 1. How many factors of 3 are there in here? Oh, so like, I guess like the way to figure this out is if you were to factorize this as like, you know, so many powers of 2, so many powers of 3, how many 3s would you get? Well, you have like a 3 here, and then you have a 6 here, which gives you another 1, and then you have a 9 here, which gives you another 2. So there's like a non-annoying way to count this. Well, it's sort of an annoying way to count this, 15 all the way up to like, so you're like, oh, for the 3 I get 1, for the 6 I get another 1, for the 9 I get 2, for the 12 I get 1, for the 15 I get 1, for the 18 that's in there I get 2 because it's divisible by 9. This goes like this for a while. Then at some point there's like a 27, and you're like, oh, for this one I get 3. Yeah, so like the annoying way to count this would be like, oh, why did I write it backwards? I should have written it from left to right. Yeah, let me do that. 100 factorial is like 1 times 2 times 3, 4, 5, 6, 7, 8. Why not do this? Should have got to 18. Anyway, yeah, the annoying way to count it is to be like, oh, it's 1 plus 1 plus 2 plus 1 plus 1 plus 2 plus, and then eventually you get like a 3 from the 27. That's the annoying way to count it. But like the other way to count it is, I was doing it with like these underlines before, which is actually kind of suggestive. If you have like 3, I get 1 factor, 6, I get a factor, 9, I get 2 factors, but I'll draw it like that. 12, I get 2 factors, 15, I get 2 factors, 27, I get 3 factors, but I'll draw it like this. And then instead of, counting like by columns, you can count by rows and be like, oh, actually the total number of factors of 3 is like this many, which honestly is basically like 100 over 3, right? It's like stupid integer parts. I mean, it's like the floor or the ceiling. I guess it's the floor of this. And then like count this row. Wait, why did I put a dot here for 9? You should have like a dot here for 18. This is where I'm counting the multiples of 9, which are giving me 2 factors. So I get like extra for every multiple of 9. So it's like basically 100 over 9. I guess it's exactly 11. And then like you get some even more, counting the row for like, this is like multiples of 3, of 9. This is multiples of 27. And like you get around 100 over 27 of these. It's really the floor of that. So it's what, like 3? And you even get like the row for 81, like the multiples of 81, of which there's only 1, but like that's the one where you're getting like an extra factor of 3. That like this one is accounted for by like 100 over 81 floor. Okay, cool. So does that make sense? I guess this is just like taken for granted in the statement of the problem. But yeah, I guess anyway, if you count it up, if you count up all the multiples of 3, you get like 100 over 3 plus 100 over 9 plus 100 over 27 plus 100 over 81. Okay, so if you weren't like lazy, or if you were lazy and forgot about the stupid floors, you'd be like, oh, this is like 33.3, repeating. This is like 11 point very little. This is like basically 4, but it's like 3.8 or 9 or something. This is basically 1. You like add this all up, you get like 49-ish. But I guess the truth is actually 33 plus 11 plus 3 plus 1, 48. No, it's close it's 48. Okay, so that means that if you write down like 100 factorial, prime factorization, it's like 2 to the power of something times 3 to the power of like literally 48. We just worked it out. 5 to the power of something, etc. I guess the last prime that could be in here is what, 97? Oh, okay. So then in the chat, same strategy works for 50 or any other number? Yeah, exactly. Yeah, exactly. So what was the point of this? The point of the question is, oh, to similarly count the number of factors of 3 and 50. Well, let's do it. It'll be good times. So 50 factorial is 1 times 2, 3, 4, 5, 6, 7. There's like a 9. There's like a 27 in here and like 50. So how many factors of 3 do we get? It's like, oh, we get all the multiples of 3. And then we get also an extra one for all the multiples of 9, an extra one for all the multiples of 27, which there's only 1. There's no 81 here. So like these guys add up to basically 50 divided by 3. These guys add up to basically 50 divided by 9. These guys add up to basically 50 divided by 27. That's it. So if we forgot about the fact that like, you have to floor each of these, like that's, what is this? 50 divided by 3 is 16 point something, 16.7. This is going to be like what, 5.5. This is going to be 2-ish, a little bit less than 2. I don't know, 1.9. So we add these up, we get like 21, 22.2, 24.2. This is going to be like 24.1 or something. We added these numbers up. I don't know, 24.1. I just made that up. Somebody can do it with their calculator. But I guess the actual truth is, what is floor 50 over 3? is 16. What is floor 50 over 9? It's 5. Floor 50 over 27 is 1. So if we add them up, we get 22. So, okay. Well, this 24 was not so far off. So that means that 50 factorial looks like 2 to the power of something times 3 to the power of literally 22 times 5 to the power of something. Okay, what was the point of this question? So then, okay, the point of this question was, let's say you do n choose n over 2, where n is even, just n even. And then you look at the prime factorization of this. This looks like 2 to the something times 3 to the something times 5 to the something times 7 to the something. And the claim is that this number is at most n, and like this number is at most n, this number is at most n, this number is at most n, etc. Okay, so this is the question. Okay, well, apparently all the stuff that was in the introductory part of the question must be relevant. So that was about like powers of 3 in 100 factorial and 50 factorial. So I guess the point was, if e.g. n is 100, then this is what, 100 factorial over 50 factorial, 50 factorial. Oh, and we learned, right? Like we learned how many powers of, what was this? How many powers of 3 were here? It was back here. This was like 2 to the question mark times 3 to the, what was it? 48. Cool. Blue is horrible. 2 to the question mark times 3 to the 48 times 5 to the something. Okay, and then in the denominator we had 50 factorial. Okay, it had 22. It was like 2 to the something times 3 to the 22 times 5 to the something times. And then we have another 50 factorial. So we get like 2 to the something, 3 times the 22 times 5 to the something. Right, so I guess the number of powers of 40 of 3 are like, there's 48, 22, 22. So the final answer is going to have like 2 to the something times 3 to the 48 minus 22 minus 22 times 5 to the something. Okay, so that's like, this is like 3 to the 4, which is 81. And hey, presto, that's supposed to be at most 100. Yes, it worked. So yeah, I guess the question is, was that a coincidence or what? Person who asked the question originally, any thoughts? Or anybody else? Was it a miracle?
Well, hopefully not, but yeah, I mean, you can do the same thing for any p, right? Like you can get exact terms for
right.
how many will be in the numerator. But I was having trouble dealing with the floors when I was doing that.
I see. Well, what was your thinking? Well, let me ask you this: like, could you conceive that, like, okay, here, like, you know, we had 2 22s, and when we added them up, it got pretty close to 48. Could you conceive that, like, it'd be quite far away from 48? Like if I was like, oh, I did the math and like, you know, I did all these things here and like this expression turned out, and maybe I did it with like some other numbers. It turned out to be like, you know, I don't know, 61 minus like 15 minus 15.
Yeah, not really, because I guess the numerator only has like one extra term in its prime factorization. I guess you might lose some with the floors as well, but yeah, it shouldn't be. They should be decently large.
What should be decently large?
The exponents in the denominator, like the 22s.
I see. How
like
large?
you only add 81 in the numerator. Everything else is still in the 50s, or is accounted for in 50s.
Sort of, right? Like, okay, this was kind of a mess, but like, let's see. Yeah, so maybe give me more on your thoughts here.
Well, just go back up to where I think we had the 81 in the 100 term. Yeah, so like that doesn't exist in the 50.
I guess there's not really a corresponding term. No, that's true.
Yeah, and then all the others do, and we have 2 copies of the 50. So like that was just my answer to why there should be.
I see. You're saying like corresponding to this, we got like 2 copies of 50 over 27 floor.
Yeah.
And corresponding to this, we got like 2 copies of 50. I guess I have an eraser here. 50 over 9 floor. Okay, so I mean, all right, what can you say about like 2 copies of 50 over 9 floor versus 1 copy of 100 over 9 floor?
They differ? Is it just at most 1, or
is it at most 1? Like 2 times this, like 2? You're saying is 100 over 9 floor minus 2 times 50 over 9 floor at most 1? Is this the question?
Yeah, in general, not just for this case, but yeah.
Okay, is it?
I'm not good with mental math, but give me a sec.
I mean, I guess this is 11 point something, clearly. 50 divided by 9 is like 5 point something. So it's minus 2 times like 5 point something.
Yeah, it's true here, at least.
So it's like 11 minus 2 times 5, which is equal to 1. Okay. Should we do another one? Let's do, what's our favorite number? 751. Hey, that's the class. 751. Should we do over 9? Let's do over 9. Floor minus 2 times, oh, well, it's not even. Okay, let's make it 750 then. What's half of 750? That's the hardest part. 375. All right. What is 750 divided by 9 floored?
Mm-hmm. 83.
83. Could be.
I just plugged it in.
Okay, what's 375 over 9 floored? I hope it's 41.
Yeah, it is. So yeah. It should
okay. Okay, so why? I mean, well, I'll leave this to you. Okay, let's leave it here. I leave it to you. But yeah, presuming this is true, then you're probably in good shape, right? Because like if this difference is always at most 1, and that basically means like here, wait, it didn't even happen here. What happened? Oh, because I see. Yeah. This is not 1. But this is like the contribution of several things which are at most 1. Right? Because like where does this 48 minus 22, etc. come from? Like this 48 was like a bunch of, was like, I don't know, like floor of 100 over 9 and floor of 100 over 3 and so forth. And we could compare that with the dots for the 50. Okay, so hopefully this is like the contribution of a few things which are at most 1. And it's therefore small. But yeah, I guess let's leave it there.
Yeah, that's good. Thanks.
Cool. Yeah, well, I guess our time is more or less up. Are there any like parting thoughts or final quick questions? Let me stop the video now.